So I think it was in this chapter, this section. I hope. If it's not, I will tell you what the answer was. Oh, here it is. Okay. So the issue was right here, right at the beginning. So I said that the sum of the voltages around a loop in an electric circuit have to equal 0 because you come back to the same voltage. You start at some voltage, you come around, you come back to the same point. It's got to be the same. And the issue was that in the capacitor, this was always positive because the capacitor was charged all the time. But the rate of change in the rate of change in charge is negative because we were discharging the capacitor. So I kind of double counted a negative here. So this was positive because it's always charged. This one has to be negative, but because this is already negative, I didn't need to add the extra negative sign. And so when I got through the whole problem, I realized that the exponent of so what I should have done is I should have kept this positive. So if that's positive, and I go through here, and that should be positive, and that should be positive, and that should be positive, 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 positive. So that's positive, 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 positive. So when I finally divide by positive, when I get to this point, okay, so we're just making all these things positive. That's positive. That's positive. And that's where I made it negative. I forced it to be negative because I knew it had to be, but I shouldn't have done that. So when I moved it from this positive term now to the numerator, it's now negative. So it turns out, and I said that it had to be negative. So that was the sign error, which ended up carrying through the whole thing. And I knew I made a mistake when I got to here, and I knew that it had to have a negative exponent because it wouldn't be exponential decay if it didn't have a negative exponent. Okay. Now the reason, usually I solve the problem in physics where you're charging the capacitor. And in that case, it works out. You don't have to worry. The sign doesn't, it kind of falls out automatically. But since that was the first, I told you that was the first time we'd done that experiment in class. So there's always mistakes you make when you. Oh, it's already in use. I don't want that one. I wanted this one. 7.1. There we go. Okay. So chapter 7.1 is kind of needs to be there to lead into 7.2 and 7.3, which is we're going to spend the majority of the time. We're probably going to spend 2 weeks on 2 sections. We'll spend like a day on this section. So the topic is finding the area of the region between 2 curves. So what you see is a picture of a graph, and there's 2 functions. There's f of x and there's g of x. And what we're looking for is the area between those 2 curves between x equals a and x equals b. Now what we've done in the past when we've done the integral, it's the area between a curve and the x-axis. So you might think, well, if I find the area from this curve to the x-axis, which is the integral of g of x, and then I find the area between f of x and the x-axis, which is the integral. If I take the difference between the area from here to the top curve and I subtract the area from here to the bottom curve, then I'll find the area in between, which is the right answer. Okay, so that's pretty much it for this section. That's all we're going to do. Yeah. So I'll go ahead and write it out. You'll see it again, but since we're looking at the picture, let's just formalize it. So what I can say is the area between the curves I'll call that just A, is equal to the integral from A to B of f of x minus g of x dx. And what has to happen is that f of x has to always be greater than or equal to g of x. So they don't switch positions. In this case, so if they crossed in the y direction, you'd have to, it's a little more, it's not that much more complicated. You just have to reflect that difference. So the key thing is that you've got to know that f of x is always greater than g of x. How do you know that? Well, that was the next graph that says plot the functions. Okay, so it's important in these next three sections is to plot the functions so you visually know what's happening within the domain that you're interested in. Otherwise, you're going to get a negative answer. Instead of getting a positive answer, you're going to get a negative answer, which, hey, we're twins again today. Must be forensics. Is it? Oh no, I don't have them. Yeah, no, I don't like those. No. It's probably because this is my original jacket, and it didn't have pads, so as a consequence, that set the precedent.
I think the only reason I like him is because TJ had him.
Because of what?
TJ had him last year.
Oh, okay. Okay. So let's continue on. So as it says here, be prepared for a subtle message. Okay, it's not subtle. So plot the functions, either using your graphing calculator or using the software that I use. Otherwise, you're going to get the negative answer, like I did on the problem we did the day before yesterday. And there's a big difference between in my case the other day. There's a big difference between exponential growth and exponential decay. So that would be a big problem. Okay, so let's look at. I think we have an example here. So here it is. It's just reiterating what I said. Is in this case I have a function. It's a parabola, and we probably could come up with the equation based on the vertex and things like that. But as we said, the integral is the area underneath the curve between the curve and the x-axis, and the two vertical lines. And now over here, what I've got is now two curves, and the area between the curve is defined by the points where they intersect. So sometimes in these problems, they give you the two x values that you're looking at. Sometimes they give you the two curves, and you have to figure out points of intersection to define what the limits of integration are. So that's what's happening with this one. So there's two curves, f of x and g of x, and because the points of intersection are at x equals 1.5 and 4.5, those are going to be the limits of integration, and because I plotted the graphs, I know that g of x is greater than f of x in this case, so I place that first. You don't need to write all this stuff down. It's just, let's just look at a problem. So find the area between the curves y equals x over 2 and y equals x plus 1 between x equals 0 and x equals 1. So as I said, the first thing you need to do is plot the functions. So I'm going to plot the functions using my graphing program. And let's see what they are. So One function is y over x. Y over 2, sorry. X over 2. X over 2. So if it's y over 2, wouldn't be. Okay, and the other one is x plus 1. So they're just two linear functions, x plus 1. And I'm going to plot them between, they say the limits are between 0 and 4, so I'm going to do it between -1 and 5, just so we have some different part here. So there it is. And let me just zoom out a little bit, the x direction. And what I'm going to do is take a picture of that and put it on my smartboard. So here it is. Okay, so now that I have those two functions, I can identify the x values that I'm going between, which is 0. So I'm going to draw a vertical line here. And x equals 4, which is right here. And the blue curve is, the blue curve is y equals x plus 1, and the red curve is y equals x divided by 2. And as a consequence, when I calculate the area, I'm looking for this area. And the one that's on the top is x plus 1. So when I calculate, if I want to calculate the area between those two curves, it's just going to be the integral from 0 to 4, and you put the the function that is greater on the interval first, and you subtract the function that is less over the interval second, and you multiply that whole thing by dx. So if I did just the first part, x plus 1, that would be the area between the blue curve and the x-axis. If I did x over 2, it's the red curve, that would be between the area of the red curve and the x-axis. By subtracting it, I find the area between the two curves. So once I have it set up, it's just a simple integration. So the first thing you want to do is, a lot of times you can combine like terms. So we've got x and we've got x over 2, so we can combine those two. So we get x over 2 plus 1 times dx. And then we just use the power rule integration, so we'll get 1/2 from here times x squared over 2, and from here we'll just get x. And because it's a definite integral, we don't add an arbitrary constant. We put our vertical line, put in our limits of integration. And let's just simplify it before we plug anything in. So we have x squared over 4 plus x evaluated between 0 and 4. And the final step is to plug in the upper limits into the equation and subtract the lower limit plugged into the equation, which turns out to be 0. So this is 16 divided by 4, so you get 4 plus 4, which is 8. So that's the area between the two curves. Okay, so that's a key thing. Or you get, if you did them in the opposite direction, you get an answer of -8, and you should always get positive answers. Now, this is don't write this down. This is just kind of something I kind of thought about, because I was thinking, you know, if you had we've got this x plus 1 minus x over 2. That was the original problem, this one here. And I thought, well, what if you switched the x over 2, or if you took the 1, the constant, and grouped it with the second term, the x over 2 variable. So it's plus 1 in this one. So I'm subtracting the second thing. So if I subtract a negative, it becomes positive. So these are equivalent statements. And so the first term, x, could be y equals x. That's a function. And the second term would be y equals x minus 2, x over 2 minus 1. And if you plot those two functions, they look like this. And you should get the same answer because all I did was just rearrange stuff. And it makes sense when you look at it. It makes sense that they should work out because all that a rearrangement of the numbers in that equation did was basically shift this whole thing down 1 unit. So instead of y equals x plus 1, I have y equals x. Instead of y equals x over 2, I have y equals x over 2 minus 1. Both of those translate the function 1 unit, and so since everything gets moved down, the relative position of the two curves is the same, and therefore the area should be the same. One thing you'll notice is that the blue curve is below the x-axis, and so you say, well, is that valid or not? And the answer is yeah, it doesn't matter. When you're subtracting, when you're looking for the area between two curves, they don't have to both be above the x-axis. They could be, both of them could be below the x-axis. One could be below the x-axis and one above. It doesn't matter. Part of it could be above the x-axis. All you're worried about is just the relative position of the two functions, the two lines. So. Okay, so here's the next problem. So this is using trig functions. So the question was, what is the area between the curve, the secant squared of x, and the cosine of x between negative pi over 4 and positive pi over 4? So if you didn't have the graph, that's how the problem would be stated. So let me write it down as if you haven't seen any of this yet. Just so the problem might say something like, find the area between the curves y equals secant squared of x and y equals whatever the other one was, cosine of x, between x equals negative pi over 4 and x equals positive pi over 4. So at that point, you really, unless you're some math savant or something, you may not know which function is greater, which one is above the other one. So obviously, it's critical that you plot these things. I mean, you could plug some numbers in and check them out. If you did it x equals 0, you'd find out they're equal to each other. You could try x equals negative pi over 4 and plug it in and find which one's greater. But those are just single points, so it's always better to just plot it out. So I plotted it out like this, and the red curve is the secant squared of x, and the blue curve is the cosine of x. And what they're looking for is the area between the two curves between negative pi over 4 and positive pi over 4. And so from that we know the secant squared is the larger of the two during the entire domain. And so I could write the integral from the negative pi over 4 to positive pi over 4 of the secant squared, which is the one on top, minus cosine of x, which is the one on the bottom. But because I've plotted them, I can also notice that there's symmetry involved. And therefore, I really could just take twice the area for either one of the wings here. So that would be a lot easier. For one thing, because I'm integrating from 0, and a lot of times when you integrate with the lower limit being 0, the terms go to 0, or they go to something easy. So I'm going to take advantage of symmetry here. So there's two things we gained out of plotting it. One was to know which one we subtract from which one, and that we can use symmetry. So we'll go ahead and do the problem. So how do we know what the integral of the secant squared is? We go to the book and we say, hey, there's a integral in there. Turns out that's the tangent. So the integral of the secant squared is the tangent. The integral of the cosine is the sine. And we'd evaluate that between 0 and pi over 4. So actually they do go to 0. The secant of 0 is 1 and the cosine of 0 is 1, but the tangent of 0 is 0 and the sine of 0 is 0. So when we stick this in, we plug in the upper limits. So we'd have the tangent of pi over 4 minus the sine of pi over 4. And then we subtract 2 times the tangent of 0 minus the sine of 0. These are 0. The tangent of pi over 4 is 1. And the sine of pi over 4 is going to be equal to a half. So that's 2 times a half, which is 1. So the area between those two curves is 1 unit. Piece of cake. Okay, we'll come back to that one. So that was in those cases we were given the limits. The other cases where you're not given limits, you just said what's the area between the two curves, and for that you have to find the points of intersection. So if somebody told me find the area between the curves x times x squared minus 3x plus 3 and the curve g of x equals x squared, then I would, and they didn't give me any limits, I'd say, oh, I need to find out where they intersect. So you can, if you plotted it, you could do it graphically, but ultimately you have to do it analytically. So I've plotted the curve. It looks like the red curve is greater than the blue curve. You guys are going, what's going on? Graduation? Oh, what's that? What it was? Okay. 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 Yeah, yeah, okay. So Martha and I have a date for Saturday. Part of the date does not include going to the game. She's going to a friend's. I'm coming to the game, but she got an email back from her. There's well, actually, you guys might. Did you ever have Mrs. Cruz? Did you ever know of Mrs. Cruz? Yeah. So she's going to see Ms. Karen Cruz, and did you have her for class? 3rd grade? Okay. Yeah. So she's doing well. Martha usually sees her once or twice a year when she goes over to Roanoke. So I'm not sure if she's dropping me off or I'm dropping her off. But she lives just around the corner from Botetourt when she retired. Anyway. So anyway, it looks like the red curve is greater than the blue curve. So let's verify that it looks like it intersects at x equals 0 and x equals 1. Yeah, I think my older daughter Jennifer had Mrs. Cruz when she was teaching at Callahan, and then she moved to Sharon after that. Yeah, Jennifer ended up going ahead a grade for math in elementary school. I think that was when she had Mrs. Cruz. Okay, so to find the intersection of any two functions is you just set them equal to each other and then solve for the values of x where they're equal to each other. So we're going to set x times x squared minus 3x plus 3 equal to x squared. So we're going to multiply the whole thing out. So we'll get x cubed minus 3x squared plus 3x is equal to x squared. We'll subtract x squared from both sides. So we'll get x cubed minus 4x squared plus 3x equals 0. We'll factor out an x. So we get x times x squared minus 4x plus 3. And then we can factor the term in here, and you'll get x minus 3 and x minus 1. So it says we have 3 points of intersection, x equals 0, x equals 1, and x equals 3. So I see 2 of them, right? You see 0 and 1, but it actually turns out there's a third point, which we didn't see because I didn't zoom out enough. So if you actually zoom out and look at these two functions somewhere here, there we go. So it actually does have 3 points of intersection. So as a consequence, you actually have to have two integrals. One for the first part where the red curve is above the blue curve, and another integral when the blue curve is above the red curve. So again, and this is where it's super critical to know which curve is above the other. So for the first interval, it looks like that's the cubed function. So the cubed function we'll have as the first function, and the squared function is the second function. And then it flips around. So I think, I'm not sure what this, I forgot what this little thing says right down here. Pull. Oops, that didn't work. Oh, yeah, okay, that was just to remind me of something. Here's the functions. So what we'll do is we'll integrate from 0 to 1. In this case, this is the, let's go back to the curve again because I forgot. That's the red curve. Oh, it's color-coded. How about that? Okay, so we're going to have x times x squared minus 3x plus 3. That's the top curve. Subtract the bottom curve. Then we're going to integrate from 1 to 3, which is the next interval. So now it's going to be x squared is the top curve, and then we're going to subtract the bottom curve. So now I'm going to ask you guys to solve that. So you're give me a break, give you a break from listening to me. So basically, what you're going to do is you're going to multiply it out, combine like terms, integrate using. They're all just polynomials. You know how to do that. Once you integrate it, evaluate the functions at the limits. Make them fractions. There'll be fractions involved, so try to leave as a fraction and not as a, don't use your calculator to do the fractions. It'll probably take you 5 or 10 minutes to do that. So I need like timed handcuffs or something, so it'll stop me from doing things early. I have to realize that you guys are not as fast at doing these as I am because I have a lot more practice. Yeah, what I need to do is bring up my cell phone and read the news or something. So when you simplify it, you get x cubed minus 4x squared plus 3x, and not coincidentally, x cubed minus 4x squared plus 3x. It's the same thing you get over here, because when you set these equal to each other, it's the same as subtracting this from that. So I already had my answer, and the other thing too is that the second one is just the negative of the first one. They just get switched positions. So when I didn't actually go in here. If you go in here and actually do it, you will get the right answer: negative 3x cubed plus 4x squared minus 3x. But because I knew from experience, all it did was change the signs of all the three terms. So that was the. So now that if you have those wrong, you can correct them and then now integrate by adding 1 to the exponent and dividing by the new exponent. Okay, Elias. Selfie time. No, just kidding. No, just kidding. I got to post it on my Instagram.
So we have to take a picture after class.
Do we? I don't have a bow tie though. Do you bring an extra bow tie one day and I'll. Do you have an extra bow tie?
Probably.
Yeah, we could both look. Next time you wear it, let me know next time you're wearing that, and we'll bring an extra bow tie, and we'll. We have about the same color hair, except I have gray and you don't. Uh-oh. I don't think I brought my calculator. Oh well. Let's see. 27, 9, 36. Anybody get that? Did I make it? You did? Did I get it right? Okay. Yeah, there's so many places you can go wrong. So the answer is 37/12 apparently. If Evan says it's 37/12, it's 37/12. So once you simplify it, you integrate it. And again, these are just negatives of each other, so I did that. And then you plug in the upper limit here, 1, so that's the top line. If you plug in 0, you get 0, which is the thing in the parentheses. Then you plug in 3 into this one, which is the second line, and you plug in 1, which is the third line, and you subtract the lower limit from the upper limit. So once you plug all that stuff in, you get these 9 different fractions or something. And what I did, I mean, there's all different ways of doing it. Since I didn't have my calculator, I was trying to figure it out otherwise. But what I did was I combined the quarter and the 2 quarters together to get a half, and the 2 -4/3 to get -8/3, and the 2 3/2 to get 6/2. So that was, I combined the first and the last line, and then I had the second line here. And then I said, oh, this simplifies down to 3. I've got a half here, but then I've got 27 halves. So that, by combining those two, I got something that I could simplify down. This is 13. So I took 3 plus 36, which is 39, minus 13, which is 26. And then I combined these. Well, I didn't combine those two. So then I ended up with just 3 terms, one that was a third, one that was a fourth, and one that was a whole number. And then I found the common denominator of 12. So I multiplied the first term by 4, the second term by 3, and the third term by 12 to get everything in twelfths. So I added them all together, and I got 37/12. Okay. So I'm gonna skip over a few things here and just assign the homework for this section before I forget.